on, I'll do introductions, Sunmee, and then I'll turn it over to you. And we're pretty informal here, so if there are questions during the presentation, I can monitor the chat, or people can just unmute themselves and ask a question. I don't think we're that big a group, or we can have questions at the end as well. So I'm pleased to introduce to the group Dr. Sunmee Kim, who is an assistant professor in the Department of Psychology here at the University of Manitoba. She joined the department in July of 2020, and she completed her PhD at McGill University in quantitative psychology and modeling. And prior to that, she completed her master's degree in mathematical statistics at Korea University in Seoul. And Sunmee and I have started working together on some grant applications. She does some fantastic research, really interested in the application of statistical and machine learning methods in the social and behavioral sciences. Her interests include the topic of today's presentation, which is on data reduction techniques, and she'll talk about extended redundancy analysis in that area. She also is very interested in how to deal with heterogeneity in data, either through the use of clustering methods and also with recursive partitioning techniques. And Sunmee has worked in a variety of areas of research, in substance use, in looking at genetic variants as well, psychological well-being, cognitive factors related to aging. We've started to do some grant applications together, really looking at recursive partitioning techniques when we look at patient-reported outcome measures and other self-reported measures. And that's a strong area of interest. So Sunmee, with that, I'll turn it over to you. And thanks again for joining the Machine Learning Special Interest Group to present today.
Oh, thank you so much for a great introduction. I feel very honored. So yeah, good morning, everyone. My name is Sunmee Kim. I'm a fresh graduate, as Lisa introduced, so I've been looking for my research groups and collaboration in my new position. So I want to thank you again for having me here today. Today, I will walk you through a statistical modeling framework called Extended Redundancy Analysis, ERA, and its recent extensions with some examples. So first, I will briefly introduce ERA and its practical usefulness in human health and behavioral studies, and I will summarize what I have contributed to conventional ERA based on these two recent research projects. And the first one is about a decision tree-based method for subgroup analysis in ERA. And the second one is about how to handle multiple correlated response variables in the ERA frameworks. And the summary of the presentation and conclusions and future plans will be also presented. Okay, so simply speaking, ERA is a statistical modeling framework that performs data reduction and linear regression simultaneously. I will briefly show you the details on the parameter estimation steps in ERA, but here I said simultaneously because all unknown parameters are estimated based on a single global optimization criterion in ERA. So parameters for data reduction and linear regressions are all estimated by a single least squares objective function. So that's why I said simultaneously. Anyway, in this example here, we have three different sets of predictors or predictor groups in a regression problem. And each predictor set reduces to a single circle here, and we investigate the regression relationships between the circles and the observed response variable. And in the language of ERA, these circles are called components that are fewer in number, fewer than the original predictors, and linear combinations or weighted composites of their corresponding predictor sets. So for example, we can think of an average of a set of observed predictors as a special case of ERA component with equal weights. And when each of the weights takes the value of 1, like here in this example, then it simply equals to a sum score. And of course, in ERA, these weights are not fixed like these examples. They are free parameters to estimate, and I will show you the details on the steps later in the slides. But the underlying procedure of estimating these weights is to explain the variation of the response variables as much as possible so that the extracted component explains the maximum variation of the responses. So ERA by nature works as a good prediction model. And actually, so far, I've encountered data in this format in many health and behavior studies. Data with multiple predictor sets nature. And let me give you some examples. First, imagine we are interested in the effect of body composition on some important health outcomes like the risk of a cancer. And in this database by National Cancer Institute, the concept body composition is an aggregation of these multiple body characteristics, including body fat, muscle, and bone minerals in specific body sites. Also, imagine we collect a data set in a neuroimaging study using EEG technique, then the data set itself is actually a collection of hundreds of voxels in a 3D brain map, and a cluster or group of voxels represents a particular brain region like hippocampus or prefrontal cortex. And let me give you one last example using the University of Michigan Health and Retirement Study. This HRS is a longitudinal panel study regarding work, aging, and retirement in American older adults. It has more than 10 different time points since 2002. And this domain of questions, physical measures and biomarkers, for example, include these 3 subdomains: physical health, physical performance, and biomarkers. And each of them again includes 5 to 30 different interview measured observed variables. So if we are interested in the cognitive performance or cognitive changes in older adults in relation to their physical health level and the amount of physical activities and biomarkers of aging and health, this ERA structure can be useful because we can include the observed measures as a predictor set of each subdomain. So I've shown that we often encounter data in this ERA format where we are required to reflect the nature of data structure in dimensionality reduction procedure. So when we have sets of predictors falling into predefined categories based on some domain-specific knowledge, when we are required to reduce the dimensionality of the original predictors based on some field-specific knowledge, then ERA is a good choice compared to other regression-based models because it has an embedded dimensionality procedure in a regression problem. And actually, the greatest benefit of this way of defining predictor component sets is that it guarantees the interpretability of the reduced dimension, I mean the extracted component. And this allows us to achieve interpretable dimension reduction for regression and prediction problem. So we have more parsimonious and interpretable description of original predictors by using the components. And this also gives us a benefit to the interpretability of the final regression model, right? It seems simpler to interpret these 3 regression coefficients instead of interpreting all of these errors over here. And it's also beneficial from a mathematical point of view because the components are orthogonal to each other. So we can avoid possible multiple linearity in a high dimensional regression problem. And we don't need to get rid of any original predictors to avoid this multiple linearity issue. Technically, the ERA model can be expressed as this equation here, and the model includes 2 sets of parameters, component weights and regression coefficients. And each component weights here represents the contribution of each predictor to obtain or form its components, and each regression coefficient quantifies the effect of each component on the response variable. And in the very basic ERA format, these 2 sets of unknown parameters are estimated by minimizing this least squares objective function. I will not go into too much details about the parameter estimation and statistical inference in ERA, but if we view ERA as a case of linear model, where we just try to find a function or model parameters based on the given observed values of X predictor, we can find the parameter estimates by least squares when the outcome variable, response variable is continuous. And if we assume a binary or count response variable from an exponential family distribution, for example, we can utilize maximum likelihood estimates for parameters to find out to estimate parameters. And statistical inference also can be parametric and non-parametric. And here I will show you the parameter estimation steps for this case over here, because it will be related to the method I will show you later in this presentation. But if the ERA model assumes an exponential family distribution, then we can define the log likelihood for a known function beta over here, and then we maximize this by an iterative method where each step involves solving this least squares problem of this defined objective function here over here to update each set of ERA parameters. And we repeat these steps until we reaches to a convergence. So far, I've reviewed the main idea behind the ERA, and now I'd like to introduce new extensions of ERA. And the first one we will look at is recursive partitioning of ERA, which automatically identifies subgroups of respondents given an ERA model. And for this, let me first illustrate the real-world data using the data set from this data repository. The data set I will use today is from the National Survey on Drug Use and Health, Nsdh. And this is a series of annual survey by the US Health Department. And each year it provides information on American adults' substance use and their psychological and socio-demographic characteristics. And those public release data sets are easy to access. You don't need to request any licenses to get the data sets from this repository. So there have been many research papers regarding the predictors of the nicotine dependence of American adults. And this is the pairwise scatter plot from the Nsdh in 2012 survey year. And here you can see some of the predictors are highly correlated to each other. And this causes multicollinearity issue in a conventional regression model. And as you know, multicollinearity affects the standard error estimation of the parameters. So the multicollinearity problem affects the estimated coefficients and their p-values, but actually it doesn't influence much the precision of the outcome variable, I mean predicted outcomes, and the goodness of the statistics as well. So it's your choice. If the primary goal of data analysis is to predict the outcome variable as accurate as possible, and if you don't need to understand the significance of estimated coefficients, then you don't need to reduce severe multicollinearity. But I found in many studies in social and behavior sciences, we care the interpretability of the model. We want to have correctly estimated coefficients and their significance to explain the impact of each predictor on the outcome variable of interest. So the model here is useful because it avoids
Oh, Sunmee, you're just cutting in and out a bit.
Sorry, what did you say?
Oh, you're just cutting in and out a little bit, just so you know.
You
lost about 15 seconds there.
Yeah.
15 seconds, okay. So that one, actually that 15 second was an important one because I was explaining how ERA is useful for this example. So here, ERA is useful because we can avoid the multicollinearity issue based on these orthogonal independent components. And then the interpretation is also very handy because of the smaller number of components for the regression problem. And here to see the impact of substance initiation ages on nicotine dependence, we just can interpret this regression coefficients where this component is just a weighted summary of the initiation ages of these three different substances. But in this ERA application, subgroup analysis so population study two subgroups that might not be similar to each other in their nicotine use patterns, especially with respect to these socio-demographic characteristics. And actually, investigating such parameter differences or parameter changes across age, gender, or ethnicity is common practice in many social and behavior studies. And in this talk today, I will call the subgroups of respondents involving different parameter estimates covariate dependent heterogeneous subgroups. So for example, in this childhood obesity study, where a predictor called health-related quality of life was considered, the stiffness of regression is not the same for girls and boys, meaning that a gender-dependent heterogeneity was present in this regression relationships. And here I brought a few things we paid special attention when developing a subgroup analysis method for ERA. From what I understand in practice, subgroups are often predefined by researchers, like male versus female using a covariate gender ahead of data analysis. But we wanted to avoid this because patterns of heterogeneity, like the stiffness regression model here, usually depends a lot on the specified statistical model used. So it's not encouraged to determine which covariate to use to split the study population. And there are several more important decision-making steps for subgroup identifications, like which covariates to use for splitting, data splitting, and how they interact with each other, and what are the cutoff values of each of the covariates. So in developing the first ERA extension for
Oh, we just lost you again.
Sorry, how about now?
Yeah, we hear
Yeah.
you. Just start with this slide again.
Yeah.
Sorry, the internet is not good here. I'm sorry. So anyway, in this paper over here, we propose to combine ERA and a recursive partitioning method in a single framework. And the original MOP procedure proposed by Xilis et al. Integrates a statistical model into a repetitive data partitioning procedure. So in this example over here, the statistical model used is a simple linear regression, and then the MOP procedure finds subgroups using a set of auxiliary covariates. So in this MOP procedure, in addition to predictors and response variables for the statistical model used, we prepare another set of variables as a data partitioning covariates. So in this proposed method, we use a set of covariate sociodemographic variables as a data partitioning variables, and the method aims to automatically identify the subgroups given a specified ERA model. And each identified subgroup involves its own ERA parameters, component weights, and regression coefficients. And we can see how ERA parameters differ across these covariate-defined subgroups. And of course, we can compare the relative sizes of the estimated parameters, because the parameter estimates in ERA are standardized ones. And in the diagram, each internal node here represents node here represents the selected partitioning covariates that classifies respondents. And note that the classification can be categories like female and male and numeric here. So in this example, the entire observation are first partitioned into people aged up to 30, and then younger group is further split by gender. And technically, how to select these partitioning covariates and how to decide the cutoff values are achieved using a parametric test called parameter instability tests. And briefly speaking, this test captures the amount of parameter fluctuation, parameter differences with respect to the value. Order. Sorry.
Yeah.
Are you hearing me now?
Yeah, we just lost that last little bit.
Yeah. So after fitting the ERA model, we can calculate the empirical score contributions, and then we reorder these n different score contributions by the order of a partitioning covariate, for example, age over here. The underlying procedure of how to calculate the test statistics in parameter instability tests is like this. If no age-dependent heterogeneity is present, then these score contributions should fluctuate randomly around their means, regardless of the order of how they were ordered or sorted by the age over here. But if there is age-dependent heterogeneity, like this figure over here, around 30 years here, then a structured deviation from the mean will be detected, and then this will be captured in the test statistics in parameter instability test. And we do this procedure for each and every covariates considered, and then select the covariate that is most associated with the parameter differences at the current stage of data partitioning is selected for the partitioning observations. So in this Nsdh data analysis, we considered these 4 sociodemographic variables as partitioning covariates. And after fitting this ERA model to entire observations, the method continues the parameter instability test for these covariates. And we can see at node number 1, the first partitioning stage, ethnicity among these 4 was most associated with parameter instability, so selected as the first partitioning covariate. And we repeat this procedure. And then this is the final solution of the proposed method. And the method identified 3 subgroups. And the benefit of this tree diagram is here. We can easily understand which covariates are associated with parameter differences. And we can see how each subgroup can be characterized by the combinations of the covariates. So for example, in this group over here, include young white respondents aged up to 24.5. And these values at each end node are the regression coefficients of the ERA model over here. And as I mentioned earlier, we can compare the relative sizes of the regression coefficients. And in this analysis, substance initiation age and the socioeconomic status, they had the largest effect on the younger white groups, but the mental health was most associated, had the largest effect in the group of older white groups. And in the beginning, I randomly divided the data set into two disjoint sub-data set just to validate the generalizability of the method. And as you can see, very similar results were obtained from the training learning set and validation sets. And notice even the cutoff value for the continuous covariate was the same in both training and test sets. And this suggests the proposed method was reliable in detecting the subgroups and was not prone to overfitting. And I didn't show the results of the simulation, but in the paper, you also can find out the simulation results of the type 1 error, power, and the classification accuracy of the proposed model as well. So far, I've discussed that defining subgroups ahead of data analysis can be challenging because it's hard to fully understand which covariates interact with each other in a given data and statistical model. So the main interest was how to automatically find out covariate-dependent subgroups of respondents given a specified ERA model. So I adopted a model-based recursive partitioning procedure for the data partitioning in ERA, and it has many advantages, like it is easy to interpret the subgroups characteristics, and it is easy to compare estimated ERA parameters across the identified subgroups. And now I would like to briefly mention another recently developed ERA extensions for multiple correlated response variables. So in the second extension, we still consider the same set of predictors from the previous examples to see the effect of these predictors on the use of multiple substances. So according to the US Health Department, the vast majority of substance users use more than one substance, showing the co-use of substances are very common in the United States. And the top 3 most used substances include cigarette, alcohol, and marijuana. So in the second ERA extension, the research question that we wanted to answer is how to simultaneously analyze the use of multiple substances in a single model. And actually, the motivation of the second extension dates back to 2017, we had a collaborative project with biostatisticians from South Korea. And at the time we needed handle these types and correlated types of Bullock syndrome based on like thousands of genetic variants as predictors. And at the time, ERA was already extended for multiple response variables, but that one has a distributional assumption. I mean, the existing method assumes multivariate Gaussian distribution for the responses. So, but in this application, these outcome variables, they not follow multivariate Gaussian distribution. So we needed to relax the distribution assumption. So I proposed a new ERA extension that relaxes the covariance structure assumption of the multiple responses. So here the main question is how we can address the unknown covariance structure between the response variables. But the true covariance structure is often unknown in practice. So in the second ERA extension, I adopted generalized estimated equations GEE to specify the covariance structure of multiple correlated responses using the working covariance matrix. In the GEE procedure, the covariance matrix is specified by a working correlation matrix over here. And here I'm showing a commonly used working correlation structures. So for example, in compound symmetry, we assume that the correlation between any pair of responses is always the same, where here the unstructured estimates or all pairs of correlations separately. And actually the main advantage of adopting GEE procedure is that parameter estimates are robust regardless of the specification of the covariance structure. And we will see this in the empirical example later in this presentation. So technically, the proposed method aims to estimate both ERA parameters and GEE parameters in an iterative manner by minimizing this objective penalized least squares criterion. And here, as you can see, this objective function adopts bridge type regularization. Because the motivation was about like thousands of rare variants as a predictor and lots of variables in the outcome variable side as well. So we adopted the regularization techniques for both part of the parameter estimations. And here I brought the results from the real data analysis using the Nsdh example again. And actually many previous studies suggested the co-occurrence of these three substances are very common, but in this present data, there was actually no strong association between the substances. And this regression and speaking procedure. Here, the way we select the best working correlation structure is based on QIC over here, and this is a modified AIC type criterion for GEE method, which is that a smaller value indicates better fit and greater parsimony. And here in this example, independent and exchangeable resulted in the same QIC value. So the more parsimonious of the two was chosen as the final one. And the regularization strength were decided using cross-validation. And in the final model, there was no regularization and regression coefficients, but slight regularization and component weights. And this table summarizes the estimated regression coefficients for each type of correlation structures. And the main reason of showing this table is to show, regardless of the specification of covariance structure, we can still have quite a consistent, robust estimate, parameter estimate using this method over here. So here, let's look at how we can interpret the obtained regression coefficients. And here, the negative association between the first component and both cigarette use and alcohol use indicated a younger age of substance initiation was associated with an increased number of cigarettes smoked and alcohol beverage consumed, but larger effects for cigarette use. And worse mental health status was associated with more days of marijuana use only in this data analysis example. And finally, American adults with lower levels of socioeconomic status were found to report greater levels of both cigarettes smoked and days of marijuana use, where cigarette use was more strongly associated with the lower SCS levels. So here I can summarize the advantages of the second extension of ERA. First, parameter estimates are consistent regardless of the defined covariance structure, so we can relax the assumptions of correctly specified covariance structure. And GEE is an extension of generalized linear models, so we can handle various types of response variables. And the proposed method automatically controls for the model complexity by including the rich type regularization penalties. So far, I've briefly discussed methodological contributions that I've made to conventional ERA, and I wanted to highlight ERA as a useful and efficient predictive modeling tool for researchers in the fields of human behavior and health studies. And I also discussed two contributions I made to the method. And in the first extension, partitioning covariates and cutoff values were found automatically given a specified ERA model. And and in all my study, I aim to obtain a better ERA model that returns results can be easily understood by domain experts while finding the right amount of complexity in a data-driven manner. So moving forward, I plan to advance or technically refine the first extension from a single tree to a forest to address high variability problem in a recursive partitioning method. So the most widely used technique in machine learning is bootstrap aggregation or bagging. So I've been thinking of applying this concept to the ERA3 methods, and this is just a sketch for an ERA forest idea. So each ERA tree is built upon a random bootstrap sample of the original data, and I think we can get a more stable and less overfitted results by using this bagging approach. And since last summer, I'm also in the process of applying the second extension of ERA into the multi-level modeling framework to see some important between cluster or between persons differences. And another big research topic for the second extension is missing value imputation. Missing data are a common problem in many studies dealing with multiple grouped analysis, especially so. I think we're refining the approach to be further studied. So I'm a quantitative psychologist, and as you can guess from my research work I presented today, I have been interested in developing new techniques to relax the assumptions or restrictions of current method we have in the field of psychology and related fields. And I believe the important role of quantitative people is to bridge the gap between textbook statistics knowledge and research questions in practice. And we are at an exciting moment in the history of behavior sciences because the recent technical advances in measuring human behavior and psychological traits are really amazing. So I hope I can continue to develop methods for these new types of data. Yeah, thank you so much for your time. And Dr. Hung-Sun Hwang is my PhD supervisor. So most of my work are the work I did together with my PhD supervisor. And I'm sorry for the internet interruptions. And thank you for your time today.
Great, thanks, Sunmee. The great presentation, very clear, and I'm sure lots of questions that will come from that. I'll start off with a question about, in the examples that you've given, you know, I'm thinking about how many predictors for each of the components, and particularly when you were talking about that example with the SNPs and the components representing the genes, any decision making around how many predictors associated with each of those components and how you make that assessment?
So usually when we apply ERA to those like genetic variance examples, we usually include all the predictors shown in the previous research. They are actually shared genetic information maps in each of the genetic data repository. So we started from the map provided by the data repository, and then we usually address the regularization for the predictors here. So in the examples of like HRS and other social science examples, we have a very clear numbers of predictors and components. But in this type of a large number of genetic variant example, we usually include everything in the model and then do the regularization, usually based on rich type regularization, because most of the time the interest is just to get the most accurate prediction model. So we just include everything and then put some regularizations and then get the results. Yeah.
Great, thanks. I'll open it up to others for questions.
I'll jump in quick. Thanks again, great talk. And you were speaking my language from the beginning, you know, body composition, bone density, holy smoke. I'm not sure if you put that in for my benefit, but yeah, that's my language. When I heard listening to, you know, dimensionality reduction, data reduction, of course, you're thinking PCA and those types of approaches. And problem with PCA is interpretability. You get these orthogonal vectors, and yeah, okay, what do they mean? Really, really hard. And so what I really like about your approach is interpretability. I'm not sure if you have any comments about other data reduction techniques versus this. The other thing I was wondering though is the component sets assume that all of the input variables are mutually exclusive from what I can see. Maybe that's not true, but if you have a primary variable, for example, age, that might mediate its effect through more than one component set, is that possible with the ERA?
I think actually my Zoom was frozen a little bit, so I missed your second example. So I heard until mutually.
Yeah. So what the question is, what if you have a primary variable like age that might mediate its effect through more than one component set? Do you have to construct the component set so they're mutually exclusive, or not?
Oh, so to answer to the second question first, because that is actually a very interesting question of my research topics actually when I was in degree. And model specification, that is possible. We actually can connect a predictor to different components. That is mathematically possible, but I don't suggest that much because the main reason of using ERA is to get the interpretable dimensional, like interpretable reduced dimensionality compared to other dimension reduction techniques. So I would say that is technically possible. And if you have a very strong background or research questions about like multiply connected predictor and component, we still can do that. But considering, and actually we do that for the genetic variance examples actually. So sometimes SNPs can be connected into different components. So actually we can do that. But in social science examples, it seems people want to have a very clear interpretation of the components, so we avoid that.
Sure, I understand.
And to answer to the first question, oh, thank you for mentioning the other dimensionally reduction techniques. And I don't suggest PC regression, I mean principal component regression, for two reasons. First one is the interpretability, as you mentioned. So you actually don't know how to interpret the reduced dimensions. And the second one is they estimate parameters in a separate step. So you first extract all the components in a predictors only, and then connect the reduced components to explain the responses. So there are actually lots of simulation studies showing those selected PC principal components are not optimal for explaining the responses. So people suggested more advanced techniques called partially squares regression, but still this approach here is better than PC regression, but it also has a limit. I would not say a limitation, but it has the main difference between partially squares regression and ERA is first interpretability. They again don't have a specified component predictor structure. And the second one is they don't have, again, a global optimization criterion. So to calculate the overall model fit measures, it's actually hard to calculate in partially squares regression. And yeah, so I actually can send you a few simulation papers that compare the performance of ERA and the partially squares regression if you are interested. So let me know. Yeah.
Thank you very much.
Okay, we've got one online question from Conrad. My question is, does your model handle missing variables? Do you want to expand on that, Conrad?
Sure, yes. Hi, I'm Conrad. Well, I just wanted to ask about non-available variables. If for particular patients, you don't have information on a particular feature. So how does your model have the ability to handle such a situation?
So to impute missing values, there are very simple approaches that are often used in regression problems, like you estimate the missing values based on the surrounded variables, or sometimes you just simply calculate the mean of the variables, and sometimes you estimate a regression for that missing value imputation. So those very basic missing value imputation method used in any types of regression analysis can be embedded in the ERA steps.
And I think this is about, I think
For
this
the
is about,
sequence,
about variables that are actually missing.
but what do you mean by you are missing a variable?
Well, some models, like you mentioned, boosting algorithm, for example. So they are able to handle the missing variables natively. So you don't have to actually impute values using mean or something like you mentioned, but they just, they can accept and input data with some missing variables for certain patients, for example, in this case. So from what I understand, in case of your model, you need to do standard imputation in some manner first, right?
Yeah, so I'm actually quite confused about the term missing variable, sorry. But for the missing values, I mean,
Yes, I think I meant missing values.
right?
Sorry
Okay.
if I expressed
No,
myself wrongly.
No,
Yeah,
that's fine.
So yes, as you mentioned, in ERA, we have very basic missing value imputation techniques that are used in regression, but we actually don't have any advanced techniques like based on some, MCMC method and other missing value imputation method used for GEE. So I need to refine the second extension of ERA to actually come up with more refined version of missing value imputation for GE method, because I found actually I've been working on the longitudinal data with the second extension of ERA, and I found there are lots of missing points in between the longitudinal panel study time points. So I am actually very interested in any collaborations for that missing value imputation method for ERA. So,
Great.
Thank
Okay.
you for your answer and for a great talk.
Yeah, thanks, Conrad. And with that, I think there may be additional questions, but we've run out of time for this morning. So I encourage you, those Sunmee's not that far away. She's an email away. If you have follow-up questions, because I could see that there are a few people that that this research might have connections to. Yeah. So thanks again, Sunmee, for a fantastic talk. Thanks to so many people joining for today, and we'll look forward to returning together in the fall. And Bill and I, we'll be beating the bushes to find people who want to kick us off in September.
thank you so much.
Thanks. Have a great summer, everyone.